Challenge day number 1. First two problems are we're going to determine if certain types of triangles are similar or always similar to each other. Sure, some triangles could be similar, but will they always be similar? So for number 1, are two isosceles triangles always similar? Well, could I make two isosceles triangles similar? Sure, I could. Let's say I had two isosceles triangles. I know they're isosceles if they have two congruent sides in here. Now, it could be true that these base angles are congruent to these base angles, and they could be similar. But will it be true that all isosceles triangles, that every two isosceles triangles will be similar to each other? That's another thing to explore. So let's say I've got this isosceles triangle and this isosceles triangle. So the triangle maker that I just had there automatically makes isosceles triangles, and I know that these base angles will be congruent, but will these base angles necessarily be the same as those base angles? And the answer is not always. Okay, so even though isosceles triangles have congruent base angles, there's no guarantee that those base angles, that pair of base angles will be congruent to each other. So will they always be similar? No. The pairs of base angles will not always, keyword there, always, be congruent. So now let's look at number 2. Are two right isosceles triangles always similar? Well, let's get a right isosceles. So there's just plain old isosceles. Let's transform it so that it is a right isosceles. So I'm going to just assume in here, I'm going to create this to be a 90-degree angle. And there's an isosceles right triangle. And so let me make a copy of this. Copy. No, let's duplicate. Now, those would be congruent to each other, and congruent triangles are always similar to each other because their sides are in a ratio of 1 to 1 and the angles automatically match. But what if I took this right isosceles triangle and made it larger, like so? Now, since the sides are different, I'd have to put in 2 congruent markings on here, but this is still a right isosceles triangle, and this is a right isosceles triangle. Well, now we come to the same decision that we were trying to do in number 1. These base angles will be congruent to each other, but will these base angles also be the same? And there's a difference here when we're talking about just plain old isosceles triangles versus talking about right isosceles triangles. Because since we know one of these angles specifically is 90, we know the other two base angles have to be congruent, and they also have to add to be 90 degrees, which means that these specific base angles have to be 45 degrees each. And the same thing's going to apply in this bigger right isosceles triangle. These base angles have to be 45 degrees each. So then we can conclude, well, here's a set of matching 45s, and here's a set of matching 45s, and our 90s are a natural set of correspondingly congruent angles. Will two right isosceles triangles always be similar? Yes. Why? Because their angles will always be 45, 45, 90 degrees, 45 degrees, 45 degrees, 90 degrees. So angle-angle similarity exists. So there is a little difference if you tweak that isosceles triangle to be a right isosceles. Now all of a sudden we know all of the angles, and we can see that all of those angles will be a match. Number 3, solve for x. So here is the first common misconception I will see many students do. They'll look at this problem, they'll go, all right, need to solve for x. X is a side, so let's set up some ratios here. I'm going to go left side, 6 over left side, 8 plus 6 is 14, and set that equal to right side 10 over right side 10 plus x, not 10x, that means multiplication. And so we're going to cross multiply. 14 times 10 is 140, and then distribute the 6 to the 10 and the x and get 60 plus 6x. Subtract the 60 over and get 80 equals 6x, and then divide both sides by 6. So x must be, if I were to simplify this fraction, would be 40 thirds, or 13 and a third, or 13.3 repeating, and they'd go, that's my answer. And I would say, how did you know those triangles were similar? Because you are only allowed to set up a proportion if these triangles are similar. And you didn't establish that you had similar triangles first. So, backtrack. Are these triangles similar? I don't know. I don't know if these bottom sides are parallel. So I don't know if these corresponding angles are congruent. I mean, I do have a reflexive angle up here. And then immediately people start thinking, oh, look, there's side, angle, side in the small triangle. And if you look at the big triangle, there's this 14 with that angle. But then the issue comes with this right side over here. You don't know how big this right side is. It's 10 plus x, and you don't know what x is. So you don't know if these sides are proportional to these sides. So, trick question. Solve for x? We can't. Because we don't know if the triangles are similar. Gotcha. Number 4. AB has a length of 4. AE has a length of 3. BC has a length of 2. Then calculate the length of ED. So let's call this piece x right here. Now, again, people might be starting to be a little leery of how I'm setting up problems and go, I don't think we can do this problem because we don't know if it's similar, these triangles are similar. But if you notice, in the small triangle and the big triangle overall, we have a set of matching 90-degree angles. So we've got at least one set of matching angles for us. And then angle A, notice, is a reflexive angle up here. It's technically the same angle in the small triangle as it is in the big triangle. So I can make the conclusion that triangle ABE, that small one, is similar to triangle ADC. By angle-angle similarity. Okay, so I know that must be true. Now another thing I could draw in here is angle A is congruent to itself, this angle E is congruent to this angle C. Well then technically that means that this angle B, the third angle of the small triangle, really must be congruent to angle D of the big triangle, right? Because look, they're both in the middle position of our similarity statement. So those two angles must be congruent to each other. So just keep that in the back of your mind. So now that we know these triangles are similar, we can set up a proportion. So let's start with this small triangle, for instance, here. Let's do this 3 over the 4. Let's do the smaller side over the bigger side. So again, this deals with small triangle. And then this ratio over here is going to need to come from the big triangle. Now the 3, notice it's in between angle A, the 1 marked angle, and my 90-degree angle. So I need to go to my big triangle, and so the side between the 1 arc angle and the 90-degree angle would really be side AC, is its correspondingly matching side. And again, instead of using the angles there, I could look at AE. AE is the first and last letter. What's going to match up with it? AC. And AC would be 4 plus 2, which is 6. Now, the 4 from the small triangle was AB, and AB was the first and second letters, so I need to talk about side AD and the others. Side AD is this hypotenuse, which is the 3 with the x. So that side is 3 plus x. And now I can cross multiply. The 4 times 6 is 24. Distribute the 3 to the 3 plus x, and we'll get 9 plus 3x. Subtract the 9 over and get 15 equals 3x. And divide the 3 over, and we get that x is 5. Since x is 5, and that is the length of the piece that I was looking for, ED, that is my final answer. So again, realize what I did first was I established that those triangles were similar before I went to set up any proportions. Number 5. From the beginning, we are told that these triangles are in fact similar to each other. So we don't have to first verify that they are. They just are. Take my word for it. So this says, what is the length of EF? And EF is the bottom of our bigger triangle. And currently, we don't have a variable. We don't know if this is x. We don't know how it relates to these other x's. So I don't want you to assume that you know what it's really related to. So we're just going to kind of leave this blank for right now. And so what I can try to do is set up sides that I do know I could put in a proportion. So for example, I notice that these two sides here, DE and DF, well, DE and DF would have to match up to AB and AC, and there's AB and AC. So it is true that the left side will match up with the left side, the right side matches up with the right side. So let's say I go 2x minus 2, the left side of the small triangle, to the 18, the left side of the big triangle, equals the right side of the small triangle to the right side of the big triangle, and then I'm going to cross multiply. Now here's what's going to get tricky, and I'm going to write this out first. The 2x minus 2 is going to have to multiply with the x plus 2, quantity-wise here. And then going the other way, 8 times 16 is 108. But what am I going to have to do algebraically here? And I'm going to have to double distribute or FOIL the 2x minus 2 and the x plus 2. So if I took first terms, or if I really distribute the 2x to the x, I get 2x squared. 2x times that 2 would be 4x. Now distribute the negative 2, we'll get a negative 2x, and negative 2 times 2, negative 4, equals 108. And so then I get 2x squared plus 2x, because I can take my 4x minus 2x is 2x, minus 4 equals 108. And this kind of looks like a factoring problem, but before I can factor, I need to put all of my terms on one side, preferably where the square term is positive. So I'm just going to move that 108. I'm going to subtract it over to the negative 4. So altogether, I've got negative 112 equals 0. So now if we want to factor this, this actually ends up being a different kind of factoring problem. You can still do it like what's 2 times negative 112? Well, we're looking for two numbers that multiply to be negative 224, and we need them to add to be 2. So you can sit there and try to figure out what those numbers are, and you can come up with them and you can factor this like we normally factored them. But this is a special case type of problem, because I want you to notice what's so special about all three of our coefficients here is that they're all divisible by 2. So what I could do is divide everything by 2, technically including the 0, if I want to keep the laws of algebra intact here. Whatever I do to one side, I'm doing on the other. But what happens when I divide 0 by 2? I'm still going to get a 0. So this will really turn into just x squared plus 1x, or plus x, minus 56 is 112 divided by 2, still equals 0. And now this is one of our easier factoring problems, because if we just had a 1 in front of the x squared, then we're trying to find two numbers that multiply to be negative 56 and add to be 1. Well, this makes the problem easier. Instead of trying to find two numbers that multiply to be negative 224, I can see easily on this one that the numbers are going to be 8 and negative 7. They multiply to be negative 56 and add to be positive 1. So then I can set this up as x plus 8 quantity times the quantity x minus 7 equals 0. Set each one of those equal to 0, and I'll get that x equals negative 8 or x equals 7. So now let me erase some of this and get some space going in here. I'll leave the factoring part down there, okay? And so now, again, if I want to know what is the length of EF, well, I need to know how big some of these other sides are. So is x negative 8 or is x 7? Well, if x is negative 8, then this would have a side length of negative 6, and that's not possible. So x equals negative 8 is what we'd call an extraneous solution. It's an algebraic answer, but it's not an algebraic and geometric answer. So x is going to have to be 7 to give us positive side lengths. So if x was 7, then this side overall is 9. And if x is 7, then 14 minus 2, this has a length of 12. So now, really, EF is the only side out of both of these triangles that I don't know. So if I wanted to solve for EF, I could go ahead and set up a proportion to say that EF over 8, right, the bottom matches with the bottom in this case, equals, and then I can set either the right side to the right side or the left side to the left side. So would I rather work with 9 and 6 or 12 and 18? I would rather use smaller numbers. So let's go 9, because that and EF were from the same triangle, and then the 6 and the 8 were from the same triangle. If we cross multiply, we'll have 6 times EF equals 8 times 9 is 72. Divide the 6 over, and EF will have a length of 12, finally. So this problem, you can see, deals with factoring, taking answers, plugging them in, and then setting up a proportion to solve. So this is truly a more challenging problem than what you guys have seen out of the textbook. And will you see problems like this maybe on a future quiz or test? I would bank on it, yes. The last problem. It says, is triangle ABC, this smaller triangle, similar to triangle ADE, which is the great big triangle? And explain your reasoning. Well, both of these triangles use angle A perfectly, so it's a reflexive angle. And then if you look at everything else, it kind of makes us feel like they want us to go side angle side, right? But the issue is we don't know those side lengths. They just put congruent markings on there. So how do I do this problem if I don't really know how long these sides are? And so we can use some variables here. So let's call these 1 marks. Let's call this x. And that means from B to D down here is x. And this is different than these sides, so let's call these y and y. And again, because I don't know B, C, and D, E are parallel, I can't just come over here and say, let me get my y back there. I can't say that these are congruent corresponding angles. So I can't use angle. All right. So if I want to use side angle side similarity, my angle in the middle has to be equal, which it is. It's a reflexive angle. But then my sides need to be proportional. So the left side of the small triangle, x, needs to be set up as a ratio with the left side of the big triangle. So how long is this side over here? What's x plus x? 2x. That's right, 2x. And we would want to set that equal to now the ratio of the right sides. So we get the right side of the small triangle is y over the right side of the entire big triangle, which would be 2y. And so we are asking ourselves, are these two fractions really equal? And a couple things to notice. Number one, those x's will cancel, and there's really a 1 in front of here. So this is really 1/2, and these y's can cancel, and again, there's really a 1 in front of here. So is 1/2 equal to 1/2? Yes. The sides are proportional. They are in a 1:2 ratio. Another thing you could have looked at is what happens if you cross multiply? Do you get the same value? So if I took 2x times y, then I would get 2 times x times y. And what if I cross multiply the other way? What if I took 2y times x? Well, then I'd get 2 times y times x. And are these two quantities the same? Yeah, it doesn't matter which way you multiply numbers, so I can freely switch around this y and x to be x and y, and then it's a match. So now I need to officially write up my answer here. Is triangle ABC similar to triangle ADE? Yes, by side angle side similarity. The reflexive angle A is congruent to itself. So I'm establishing that I do have a set of congruent corresponding matching angles. So reflexive angle is congruent to itself. And the two sets of corresponding matching sides, right, the left and the right sides, are proportional. And I can even provide a little evidence of what that proportion was. It was a 1:2 ratio, right? Because when we canceled the x's and we canceled the y's, we saw that the small side to the large side is a 1:2. Okay, so that is my official, that proves that side-angle side similarity really does exist. And I would want you to show me this as kind of part of your evidence as your work for that particular problem. And that is all for challenge day number 1. Quiz tomorrow.